In this example, we show how to characterize modular arithmetic in the language of Hebron logic. In modular arithmetic, there are only finitely many objects. For example, in modular arithmetic with modulus 4, we would have just 4 integers, 0, 1, 2, and 3, and that's all. Our goal here is to define the addition relation. Now, admittedly, this is a modest goal, but once we see how to do this, we can use the same approach for defining other arithmetic relations as well. In order to describe modular arithmetic in Hebron logic, we adopt a signature with 4 object constants, 0, 1, 2, and 3. We use the binary relation constant next to relate each number to the next larger number. And we use the ternary plus relation constant to relate 2 numbers to their sum. That's suggested here. Representing addition using a relation constant rather than a function constant, admittedly, is a bit unconventional. However, it avoids some problems that we will discuss and solve in a later lesson. Let's start our formalization with the same relation. Here we've written out all ground sentences involving same. One positive sentence for each number and itself, and negative sentences for all other combinations. We can define next in a similar fashion. Next of 0, 1, next of 1, 2, next of 2, 3, next of 3, 0. Note that in modular arithmetic, we wrap back to 0 after we get to 3. And all the other ground items are false. Here here's another alternative to doing next. In this case, we've written out just the positive relational sentences involving this relation, one for each number and its successor. We can dispense with the negative cases, in fact, by writing just a single logical sentence. The functionality axiom shown here asserts that next is a functional relation. That is, for each number, there is just one successor. In order to see why this saves us the work of writing out the negative literals, we can write this axiom in the equivalent form shown here at the bottom. If next is true of x and an object y, then it's false of x and every other object z. Having defined same and next, we turn our attention now to plus. The addition table for modular arithmetic is the usual addition table for arbitrary integers, except that, as I mentioned before, we wrap around whenever we get past 3. For such a small arithmetic, it's really easy to write out the ground relational sentences for addition in this, as we see here. However, as with next, we can write a functionality axiom to take care of the negative sentences. Plus of xyz and plus of xyw implies that z is the same as w. That's one way to do things, but we can do, in fact, even better than that. Rather than writing out all of those ground relational sentences, we can use the language of Hebron logic to define plus in terms of next and use that definition to deduce those other sentences. The definition is shown here. First, we have an identity axiom. Adding 0 to any number results in the same number. Next, we have a successor axiom. If z is the sum of x and y, then the sum of the successor of x and y is the successor of z. And finally, we have our functional axiom, as before. One advantage of doing things this way is economy. With these sentences, we do not need the ground relational sentences about plus. They're all logically entailed by our sentences about next and these definitional sentences. A second advantage is versatility. Our sentences define plus in terms of next for arithmetic with any modulus, not just the modulus 4. The main lesson to be learned from this example is the use of equality, same in this case, in defining functionality and the importance of functionality in formalizing information in applications like arithmetic.